Let's look at the first example, example 10.1. We want to use least square technique to find the equation of the straight line that will best approximate the data in the table. The keyword is the line. Okay, so we want to find the linear equation. And what is the general look of the linear equation? When your equation is linear, the general look of it is y equals a plus bx. So what we have to find here is to find the constants a and b by using the data in that table. And there are 5 data points in the table. Okay, that is the first point, second point, all the way to the 5th point. So there are 5 points altogether. And we want to use the concept or the technique of least square approximation to use those 5 data points to get the value of a and b such that this is the linear equation that fits or that runs through this data. Okay, and with the linear equation, then there are 2 constants to be determined, a and b. So the system of normal equations will be a system of 2 equations and 2 unknowns that look like this. On the system of normal equation, I'm going to write it in the matrix form. And that spot is going to be n. In this case, n is 5 because there are 5 data points in the table. And the element in the first row, second column is summation xi. Same idea over there in that spot. The element in the second row, first column is summation of xi. And that spot, element in the second row, second column of the coefficient matrix of the system of normal equations is summation of xi squared. And that matrix, that is the coefficient matrix, is to be multiplied with the vector that has a and b that we want to find them, and equals to the right hand side, which is a vector that has 2 spots. The first spot is summation of yi, and the second spot is summation xi yi. So the look of the system of normal equations is like that, a system of 2 by 2, 2 equations and 2 unknowns, and the 2 unknowns are a and b that we have to find. If you can solve this system by using the data points given in the table, if you can solve this system to get a and b, then you can have a linear equation or a linear function that can be used to approximate the future data or even the data in the past. Okay, so those are what I need. And again, n is 5 in this case because there are 5 data points. I need the summation of all si, so I construct a table. In first column, I put I number. Okay, second column, I put all the values of si. In the next column, I put all the values of y from my table, from the given data. Okay, and then at the bottom here, I find the summation of all si value. So I add them all up. Okay, same idea in the column of yi, I add them up to get the sum of 29. That 29 is just the sum of all those numbers. Okay, I need summation of si right at that spot, second row, second column. So out of the next column, I square each xi of my first column. So I square each one of the xi, and then at the bottom, I find the summation of that column. So that is just the summation of each xi. And not only I need summation of xi, if you look to the right hand side, I need summation of xi yi. So in this column, the next column, I find the product of my si and yi for each I. For example, at I equals 1, I multiply s1 and y1 together to get 2. At I equals 2, I multiply s2 and y2 together to get 6, like that. And then out of that column, I get the summation of si yi because this spot in my system of normal equations need the sum of the product of si and yi. So in this spot is going to be 5, summation si is 15, summation si there is also 15, summation si squared, which is 55, summation yi 29 and summation of siyi is 106. So I get the system. I have it on the next slide. Okay, this is the system. Okay, that I got the coefficient matrix from the table in the previous page and also the right hand side. And you all know how to solve this system, right? You can use Gaussian elimination. You can use Jordan elimination, or whatever technique that you can think of. Just do whatever it takes to get A and B. Okay. So I showed you in using Gaussian elimination. So I divide the first row by 5 to create a leading one in that spot. First row, first column. And after I've got the leading one, I use it to get rid of 15 underneath it by performing R2 minus 15 R1. And I get a triangular system. Okay, upper triangular system. And out of excuse me, and out of that system I can solve for B and A. And I got my A as 0.1 and my B is 1.9. By knowing A and B, then I get the linear function. I got the linear function by using those 5 data points with the technique of least square approximate. Okay, and then you can see that in the graph, those points are the location of those 5 points in the table. And this straight line that you see is the straight line that has the equation of 0.1 plus, that is 0.1 plus 1.9 times x. Or you can call it as p of x. Okay, p of x. Okay, so you can see that the linear function itself doesn't pass through all the data points. Okay, it doesn't pass through all the data points, but based on what I proved to you guys on the least square technique, that is going to minimize the square of the error. So not only I predict the y for you at those s values, so in that second column are the exact value of y, and that column gives you the predicted value of y. That means I evaluate p at each xi. So by using that first degree polynomial, when I plug x as 1, I get the approximated y value or the predicted y value at s equals 1, and that is the approximate value at s equals 2 by plugging s equals 2 right there. Same idea over there in that spot is the approximate value by using the polynomial p and plug x as 3. I get the approximate solution or the approximate value of y as 5.8. But the true value or the exact value of y at that point is 7, so you have error. The error is just the difference between the exact value and the approximate value as usual. Okay, so that column gives you the error, which is the difference between the exact value and the approximate value. And then I compute the error square on the last column. And you can add this up. Add this column up, you're gonna get the total least square. You add them up, you get the total least square error. Okay, so that is the idea of using least square technique to get a linear function that can be used to approximate the future value of y.